Okay, yeah, thanks a lot, Kenichi, and thank you very much, organizers, for this opportunity to speak here. And I was struck by the logo, the poster, and I suppose it's a kind of a thing about our field that Teichmüller theory and Bers go together. So it's the Bers slice, right? So the Bers slice, I think, is going to figure, at least in words, somewhere later on in this. And it's, yeah, so that's one thing. The other thing that I was reminded of, and I think ever since we were in grad school, we've been looking at Teichmüller theory, and new trends in Teichmüller theory reminded me of this. There was some interview of Ernest Hemingway after he wrote Old Man and the Sea. And apparently the interviewer asked him, well, what does it mean? And Hemingway's response was, I wanted to write about a real old man fishing for real fish in a real sea. And if the story is real, it will mean many things to many people. So I think that's what Teichmüller theory means. It means many things to many people. And I'll focus on just one particular aspect of it, which has been emerging. And right, so I think to Teichmüller, it meant hyperbolic versus complex, and now it means many other things. So, okay, so this is really, I mean, I think, again, the other thing is that this is really Sabya's project, and I have tagged along with him for part of the story, which is more Kleinian groupy. And so I think this is, yeah, so we'll start with that. And so where does it start? I think it was, this contact between holomorphic dynamics or rational iteration of rational polynomials has made its appearance in this workshop conference a couple of times, once during Professor Shiga's talk, and I think John mentioned it in passing at the beginning. So we'll start there. And there's this statement by Fatou, which basically says that there's this remarkable analogy between the limit sets, which for Kleinian groups, and I mean, he says that the boundary of the region of convergence, which basically means the Julia set. Yeah, so I think Fatou was not immodest enough to call his set the Fatou set, and at that point of time, I think the terminology was not well developed enough. But he's basically saying that the limit sets of Kleinian groups and Julia sets have of rational functions, they seem to have a similarity, which is probably not fortuitous, and should be put into a general theory. And what he says there is basically algebraic correspondences. Yeah? Which basically means complex analytic, multi-valued maps with more than one value, typically finitely many values. Okay, so this is 1920s, almost 100 years back. And this suggestion of Fatou lay fallow for decades, till Sullivan picked it up in the 80s, and the Sullivan dictionary, which you saw in the which you saw in the previous talk, emerged. And as John mentioned, Sullivan's approach was to draw philosophical similarities between the two sides and introduce techniques, basically quasiconformal techniques, and essentially say that, look, if there's a theorem on one side, something like that should be true on the other side, and you can pull some of that techniques through. So yeah, I think I am being recorded, but I can't. It's a quotation from, I think, André Weil. It says, these furtive caresses between fields, is what he says in French. So basically, between complex dynamics and Kleinian groups, there's, I mean, I think the dictionary kind of puts the relationship in some philosophical background, which is similar, but Fatou's question was more precise. He wanted a unification, and he suggested a framework, and the correspondence, the algebraic correspondence framework, is what I hope to just about get to by the end of this talk, and then Sabya will take over and tell you more about it. Okay, so first, what are these parallel worlds? And this is really a spelling out of the Sullivan dictionary. So on the one side, you have rational maps. On the other side, you have Kleinian groups. This is a slide which is Sabia's, and I have shamelessly plagiarized it. Okay, and then you have the Fatou set and the Julia set. Similarly, you have what in Kleinian groups world is called either the ordinary set or the domain of discontinuity versus the limit set. And then there's the Alfors finiteness theorem in Kleinian groups, which says if you have a finitely generated group, then you look at the domain of discontinuity, look at the quotient, that's a finite type surface. And the analogous statement, and this is probably one of the first successes of the Sullivan dictionary, is the no wandering domains theorem by Sullivan. So again, there's this Fuchsian space or the Teichmüller space on the Kleinian group side, and the corresponding thing in the complex dynamics world is called the space of Blaschke products or the Blaschke space. And then there are deformations of these guys, quasi-Fuchsian space versus the quasi-Blaschke space, and so on. So this is basically the notions at the top. And then there are theorems. Yeah? So there's, and it's quite significant that a lot of the theorems really came from, I think the first set of theorems came from Thurston, then Sullivan, and they were interested on both sides of this dictionary. So there's the double limit theorem, and that translates to this branch covers as rational maps and hyperbolization. I mean, there's a polynomial mating, which is an analog of the double limit theorem. There's hyperbolization of three manifolds with totally geodesic boundary, or well, with some embedded totally geodesic surface. You have realization of branch covers. You have geometric limits, and on the Kleinian group side, there's parabolic implosion, et cetera, and so on. And there are also things in terms of techniques. Quasiconformal deformations goes back to Alfors and Bers, quasiconformal surgery, and so on. Yeah? So this is a kind of an impressionistic slide telling you that there's a lot going on in the dictionary on the two sides, and the dictionary really translates words from one side to the other. And as with all dictionaries, a word with a particular connotation in a particular language, when you translate it, you don't quite get the exact connotation. There are these fuzzy edges, but there's enough overlap. And so I think it's appropriate to call this a dictionary, yeah, between the two. So now what we'll try to do is, okay, so let's first define this. So I think this has already been defined. The limit set, and I think I learned this notion from Kurt McMullen when I was a grad student. He is very fond of describing the limit set as the locus of chaotic dynamics for the Kleinian group. Yeah? And I think that point of view really comes from complex dynamics. So it's so the limit set has already been defined. You basically take a point if the group is non-elementary, and all our groups are going to be non-elementary. You look at the orbit of a point in hyperbolic 3 space, you look at its collection of accumulation points on the boundary, that's the limit set, and the complement of the limit set in the Riemann sphere is the domain of discontinuity or the ordinary set. Okay, and I'm particularly interested in surface group representations. It's a Teichmüller theory conference. Okay, so we are particularly interested in representations of surface groups into PSL2C, discrete faithful, and I'll restrict it further, and I'll demand that the limit set is topologically a circle. And these guys are the same thing as so this implies once it's a topological circle, it splits the Riemann sphere into two open disks and the limit set itself. And the representation of the group, rho of pi 1s, it acts freely, properly discontinuously on the two sides, quotients it down to give you two Riemann surfaces. And the Bers simultaneous uniformization theorem says that the quasi-Fuchsian space is exactly the product of the two Teichmüller spaces. So if you have a limit set, so the quasi-Fuchsian space is going to be defined to be the collection of representations of a surface group into PSL2C such that the limit set is a topological circle and the representations are discrete faithful. Okay, so from such a representation, you get a map two Teichmüller space plus cross Teichmüller space minus. That's D plus mod gamma and D minus mod gamma. So those are two conformal structures. And Bers' simultaneous uniformization theorem says that, look, this is all that there is. So that's all. I mean, so basically you look at these representation mod conjugation, and this is the space that you get. Okay, and these are the same thing as quasi-conformal deformations of the Fuchsian representations. It's kind of similar to the way Hitchin representations are defined, except that's real and this is complex. Okay, so therefore, what do we get out of this? What we are thinking of this Bers simultaneous uniformization theorem as is a combination theorem. What are we combining? So this is a kind of a dynamical combination theorem. Dynamical in the sense of dynamics in the Riemann sphere. So you take two discrete faithful representations into PSL2R. Yeah? This is the same thing as, and this is a closed surface. So this is basically the same thing as two Riemann surfaces or two hyperbolic two manifolds closed. Let's say S is closed for now. And what this says is that you can take these two real representations, put them together, and you get a single representation into PSL2C, different Lie group. And what does it mean to say that you have actually combined them? It means that the dynamics of pi1s on the open unit disk, yeah, under via rho 1 is conformally conjugate to the action on D plus. And similarly, you look at the other representation, rho 2, and you look at that guy acting on the open unit disk, that's conformally conjugate to the action of the group on D minus. Yeah? So that's the sense in which the simultaneous uniformization theorem is a combination theorem. You have two holomorphic dynamical systems given by groups acting on the unit disk. You can put them into a common dynamical system where you have the action of one group on a Riemann sphere, no longer the unit disk, such that the Riemann sphere splits naturally into two parts, and on one part it's the first group, on the second part it's the second group. So in some sense, you should really think of this PSL2R, this representation, as actions on the open unit disk with the complex structure. So really what you're doing is you're taking complex dynamical systems and combining them here. So this is our starting point. And a similar theory exists in the context of complex dynamics. I won't get into it too much, and I think the one significant reason is that I don't know this theory particularly well, just whatever I've learned from my collaborators. So there is a way of taking two polynomial dynamics, and you do a similar thing. Let's say you have a polynomial which has Julia set, which is topologically a circle, and you can run basically the same story. Yeah? If you have a polynomial running on one side, you have a polynomial running on the other side, you put them together, you get a rational map, and that acts on the Riemann sphere. Julia set is still a circle, and you restrict the rational map to each of the two sides, you get back something which is holomorphically conjugate to the two polynomials you started off with. So this is the Duarte-Hubbard theory of mating, which was again developed in the late 80s. And it's basically this context. However, what are we doing here in the first context for the simultaneous uniformization theorem? You're taking two things which are both groups, and both are the same group. In the second, you're taking two polynomials with the same degree. So you're really picking the two things you want to put together from the same basket. Yeah? And yes? Same degree in the same principal hyperbolic component. So here the analog is, for us, it's Fuchsian groups. For the complex dynamics guys, it's the component containing Z to the D. Yeah? So that's the principal hyperbolic component. And pick two guys from there. And so a similar combination theorem can be worked out there. So these are all dynamical combination theorems as opposed to group theoretic ones. Okay, but we picked the two objects we wanted to put together from the same basket in both cases. Same kind of complex dynamic systems, yeah? Either groups or iteration of maps. And now the question is, if we want to proceed towards realizing Fatou's vision of actually putting them together in a common framework, we need to find, at least as a first step, is it really possible to interbreed these two guys? Can we interbreed? And so how to combine Fuchsian groups on the one side with polynomials on the other? Okay, yes. Yes, there is. So basically the idea is that there is something called a Moore obstruction, which is basically the same thing that I mean, you don't have points which are pinched on one side which also get pinched on the other side. That's one obstruction, but there are some others. And I mean, Sabir is much more of an expert, but I think under these conditions, when you're taking two polynomials in the same principal hyperbolic component, you can combine them. And the Julia set is still a circle, topologically a circle. There is, yes, that's right. Okay, so how do we combine these guys? And what does it even mean? I mean, so iteration of polynomials is a semi-group. Yeah? You pull back, and there's no well-defined inverse. There are many inverse branches. So how are we going to combine these guys together? So first is you have to relax your framework, but you can't, I mean, you have a group and a semi-group, so at the basic algebraic structure level, things break apart. But you want only a dynamical combination or dynamical mating of these two objects. So the first thing is you want to replace, so the group is a richer structure, it's got inverses and so on. So what you want to do is replace the group gamma by a dynamical system given by an iteration of a single map. So that's what one would like to do. So you say, you say that a single map, self-map now on the circle. So, okay, so at this stage, the story is going to become progressively more and more structured. And the first slide and the second, we are going to dwell on what Kleinian groupies like me call the topological part of the story, and the complex dynamics people like Sabia call the combinatorial part of the story. We are talking about the same thing. Yeah? It took me a while to realize that the complex dynamics people regard laminations not as topological objects, but as combinatorial objects. But that's how it is. Am I reasonably correct? Okay, so this part of the story is topological, and so really it's okay. So let's get into this. So firstly, you want to throw away some extra structure from the group, and you want to replace it by a semi-group, which means by iteration of a single multivalued map. So a map. So let's say you have a Fuchsian group gamma. Yeah? So this gamma is your Fuchsian group acting on the circle. And you say a self-map, continuous self-map for now, from the circle to the circle is orbit equivalent. So A is something that you can iterate, and you can look at pre-images. If for every point x on the circle, the gamma orbit, that means the group orbit, is the same thing as the grand orbit of x under A, which means what? You take x, you take its full forward orbit, that you take the full backward orbit of the full forward orbit. Yeah? Which means basically 2 points are regarded as lying in the same grand orbit. If you take these two guys, you iterate them forward, at some point they agree. Yeah? So that's the grand orbit. It's basically because you can't take inverses, because that inverse is multivalued. That's all. Okay, so that's orbit equivalence. And this is the weakest kind of thing that one can demand purely in terms of the orbit structure of the dynamical systems. Yeah? And if you are going to replace a group by a single map, you can't do very much better than that. So this is something that you would like to have. So we are defining essentially a map which has the potential to be mated with a z to the d. Yeah? So that's why we decided to call these matable maps derived from groups. Yeah? So something which has the potential for being combined. Yeah? So it's a self map. So it's firstly, this is the dynamical synergy between the group and the self map. Second, you want it to be kind of, if A was demanded as something that was actually complex analytic on the whole circle, then by the identity principle, if it agrees with some polynomial, it has to be the polynomial. Yeah? So you have to relax your category. And so I think the category that we went into was basically piecewise analytic, yeah? And continuous at the breakpoints, continuous. To start off with, the story is where the self map is continuous, but pieces are actually analytic. Yeah? And if you're piecewise analytic and you're orbit equivalent to a group, then it turns out that the pieces will have to come from the group. So it doesn't really matter if you put in this restriction ahead of time and say that A is piecewise Fuchsian, which means the pieces of A. Let me draw a picture here. So this is basically, I think this is going to figure somewhere. So this is a parabolic here. This is G, and this is H. So this is a thrice punctured sphere, and there are these two parabolics, yeah? So what's the piecewise Fuchsian guy? You have, so these are the pieces. So this arc here goes via G, it's got to go to here. So it's basically this side gets identified to that. Similarly, this guy here, color, this guy here, it goes to here. So basically, on this, it's G. On this, it's G inverse. Basically, here, it gets pulled up. This gets pulled down. And similar things on the other two sides, yeah? So this is an example of a piecewise Fuchsian guy. So it's defined in terms of the elements of the group. And yeah, anyway, so this is an example. So basically here there are 4 pieces. You've divided your circle into finitely many intervals. On each of those intervals, it's actually a Mobius transformation, which comes from the group. So the circle is the union of these intervals. The restriction of this single map is a group element. The group elements that are the pieces, they generate for you the Fuchsian group gamma. Further, you want it to, I mean, so this part of the story, the first two, orbit equivalence and regularity, are dictated to you in some sense as a dynamical system on the circle which inherits the dynamical properties of the Fuchsian group. Yeah? But you want to have it something which is potentially made to Z goes to Z to the D on the other side. And so for that, you just put in the minimum kind of condition that it's topologically the same thing as a covering map default, expansive covering map. So it's topologically conjugate to Z goes to Z to the D on the circle. You have to take a little bit of care. Okay, yeah, so this is a combinatorial property. This is, I mean, it's an organizational thing, and sometimes it's relaxed, but I think for all reasonable examples, you need this. Essentially, what you want is that the intervals, the partition, they form a Markov property, which means you take an interval, you map it forward, it covers finitely many of these intervals contiguously. Yeah? Need not be, I mean, the regularity, it's, so this is, you want the image of A of ij, which means basically Gj of ij, to be a full interval, full union of intervals. It could in principle, yeah, that's not that. That's the additional thing, yeah. So so you can write a matrix here. You can write a matrix where the vertices correspond to the intervals 1 through k. Okay, and then there's just, yes?
Okay, I was asking, this mapping, hey, permutes the intervals or?
It does not permute the intervals. It takes each of these intervals and maps it over finitely many intervals. So it's a it's a Mobius map. In particular, it's a continuous map.
Okay,
it takes one of these maps and it could go and land somewhere in the middle of the next guy. We don't allow that. We want it to cover a full branch collection of intervals. Okay. In particular, what follows is that the vertices, the breakpoints, go to breakpoints.
Okay, thanks.
So this is some kind of combinatorial thing that you would like to have ahead of time. Okay.
be the interval exchange transformations.
Yes, but there you are allowed to scale some of the intervals. So the intervals after you do an interval exchange, sometimes they fall in the middle.
Yeah, exactly. That's the reason why I ask you.
That's not what you're.
Okay.
Yeah.
Thanks.
Which is why there you have to, after iterating, you get a lamination or a foliation, right? That's not quite it here. Okay, and the last thing, and this is really, well, we had these breakpoints where we just demanded continuity. However, we want it to be conjugate to z goes to z power d, which means that the derivatives on the two sides should be the same. So you don't want a scale factor which is z goes to lambda z on at the tangent space level. It's z goes to 2z on one side, z goes to 3z on the other. That's something that would be bad, because you wouldn't be able to conjugate that to locally, even locally, to z goes to z power t. So this is a kind of a local local condition which is forced by the fact that you want it to be something that is mateable with z goes to z power t. This condition here is a global condition, again, from coming from the z goes to z to the d side. The first two conditions are coming from the group side, and this combinatorial property is something just to make everything consistent and have a nice picture, at least to start off with. Okay? And so this is basically a potentially mateable map, or something which is kind of forced on you by the problem. And so how would you go about actually manufacturing a mating of one of these guys with z to the d? And this is what you do. First, because this is a piecewise Mobius map, they have a natural domain of definition, which is basically look at the semicircles which hit each of these pieces at right angles at the boundaries. So you can put in these half planes. Yeah? And so you can actually define a canonical extension of this piecewise Mobius map onto this domain. So each of these guys, they could in principle get mapped over, so suppose you have one semicircle mapping over three of them, so then this arc here is going to get mapped to the geodesic between the first and the third. So it could map inside R. Yeah? So it's really a map from this domain into the whole disk. It's not necessarily invertible. Yeah? So this is a canonical extension of a piecewise Mobius map. It's defined on D bar, and this R is like an ideal polygon. It's what we decided to call a hole, because a hole is something things fall into. Yeah? So the rest of the stuff after iteration finally falls into the hole. Okay, so this is a canonical extension, and now this is a piecewise analytic object, and the only breakpoints are really at infinity, so you don't really mind. And it's continuous there. On the other side now, you look at z goes to z power d, which is just this. And then because of the topological conjugacy, you can pick a topological conjugacy between z to the d and this mateable map A. Yeah? And you can extend it to a homeomorphism now. This is just the topological part of the story. So you can extend it to a homeomorphism from the closure of the disk to the closure of the disk. Now, okay, so the topological part of the story, there are no real problems. Once you have all this topological conjugacy, you can take this piecewise Mobius map and this polynomial from d bar to d bar, and you glue them together using this homeomorphism psi. That's a conjugation. Yes? Yes? Oh, it's okay. So firstly, you want it to be topologically conjugate, because without a topological conjugacy, you can't glue the two sides. So you're thinking of, P is z to the d.
Oh, I see.
Yeah, P is z to the d.
Because then you know that P is
Right. So it's z to the d. On the circles, it's basically, this is saying on the circle, A and z to the d are topologically conjugate. So you have a topological conjugacy between them. That's all. It's forced on you. Without that, you want conformal. And we are saying, let's hypothesize topological, at least on the circle. Yeah. So yeah, exactly. So it's hypothesizing a topological conjugacy on the circle. It's a kind of assumption there. Okay. So now, so what you're really doing is, I mean, so I'm really fixing the polynomial to be z goes to z bar d on the yeah. So let's say this is the group side, and yeah, I think as a Kleinian groupie, I have a fascination for this being the part where I see the action. So this is the south pole, and this I think is the north pole. Z goes to z to z. Let me just finish this, yeah, and then I'll come back to you. So suppose you have this topological conjugacy, then you can glue. So basically you have what have you obtained after this? Because there's a topological conjugacy, you can glue using the topological conjugacy, and you get something on the lower hemisphere. It's this piecewise Fuchsian map, self-map of the disk minus R to itself. And on the upper hemisphere, it's z goes to z bar d. Yeah? And you've glued them by just a homeomorphism, so there's no holomorphicity in sight, but at least there's a topological dynamical system on the Riemann sphere, from the Riemann sphere to itself, which restricts on one part to z goes to z bar d, on the other part to this map A, which captures the dynamics of the Fuchsian group. So far, this is the end of the topological story. Yes, Chaitanya. Right.
So how does one construct
Wonderful. Good. Hold on to that question. I mean, you're basically asking, am I giving you a vacuous theory? Am I talking about compact Banach spaces over R, for instance? Right? That's what you're asking. Yeah, hold on to that. That would have been, I mean, if the answer to your question is there are no goddamn examples, then I'll be feeling very, very silly talking about it. Yeah. Okay. So that's fine. So we'll answer. So the answer is this guy is an example, and we'll tell you. I'll demystify that statement as we go on. Okay. All right. So this is the topological part of the story, and the next step is to move from topology to complex analysis, where we can basically make this whole picture complex analytic, which is the point of the Bers simultaneous uniformization theorem, which is the point of this Duadi-Hubbard mating theory. And it can be done. That's the good part of it. So this is the topological mating, and you want to upgrade this to a conformal thing. And so things which were potentially mateable are indeed mateable in the complex framework. I hate using the word category, but it's in the complex setup, complex analytic setup. Okay. So what does it say? It means that so given a mateable map, which is one of those things, which has all those conditions, and you have just z power d going from d bar to d bar, these guys can indeed be conformally mated, which means now that this topological dynamical system that you had at the end of the previous slide is topologically conjugate to a complex analytic dynamical system, yeah? Which means you have a self-map now of the Riemann sphere to itself, which now has a Julia set or a limit set, which is topologically a circle. On one side, you restrict that complex analytic self-map. It's conjugate on the northern hemisphere. It's conjugate to z co power d, yeah? Which means you remove the Julia set. That's the top side. There it's this. There it's z goes to z power d, and you look at the southern side, and there it's conjugate to, holomorphically conjugate to this canonical extension of this map A. Okay, so this piecewise Mobius map. Okay, so this is the part where you upgrade a topological or combinatorial statement to something that's complex analytic. And here, see, the thing is, it's the measurable Riemann mapping theorem that's the workhorse for the Alfors Bers. I mean, that's where all the analysis is. And so you really need, so you want to promote the topological mating to a conformal mating. So the extension of psi, yeah, that was this conjugacy, it should be a nice guy. And so here you need an essential complex analytic ingredient. And let me just say in words wherein lies the problem. The thing is, at those cusps, yeah, these points here, it's possible that the map that you get is from the Kleinian group side is only parabolic. Yeah? So which means that the derivative is 1. On the other hand, if it's z goes to z power d, and suppose it's a fixed point or whatever, I mean, then it's necessarily hyperbolic. How are you going to match those two? So there is something called this David integrability theorem. You can use Bers simultaneous uniformization theorem, the technology, except that at these points, something on one side that is hyperbolic is allowed to go to something that's parabolic on the other side. So something that has positive derivative greater than 1 is allowed to go to something which has derivative equal to 1. So and there's some other things. In this particular case, it's allowed. And so these piecewise analytic guys are indeed, via this simultaneous uniformization on steroids, you can actually upgrade and conduct this mating. So that's fine. So essentially, you can upgrade. I mean, so you have this abstract definition of a potentially matable map. If you can do it topologically, what this theorem says that if you can do it topologically, David tells you that there are no complex analytic local instructions. Okay, now to answer Chaitanya's question, this picture here is the same as this picture here. Okay, and so what is it? I mean, essentially the question is, is this just wind? Yeah? Or are there real examples? And so here is the point. So the answer is that there are indeed examples. And this goes back to work of Bowen and Caroline series. I should probably write to Caroline saying that I cited her work again today. So this is, I mean, I think their objective, this I think is work that started probably in the late 70s, early 80s. And it came from a very different kind of dynamical motivation, but very different kind of thing. It came from ergodic theory. And the focus was really on closed hyperbolic surfaces. So this, as you can see, is a genus 2 surface at its fundamental domain. So genus 2, no punctures. And they developed a symbolic coding of various words. So the thing is, in a closed surface, so what they did was they devised a self map on the boundary of the circle, a single map, which has the properties that we demand. That means orbits are the same as group orbits, except that Bowen and series were interested in measure theory as opposed to topology. So for almost every point, they required this. And they required a measure theoretic version of the statement, whereas what we require is something that's topological. So we want a topological version of the Bowen series map. And it turns out that for punctured spheres, these Bowen series maps, what are they? Essentially, so suppose you take the simplest example, the thrice punctured sphere. You have this G here and H here, which means on this, so you divide your circle into 4 arcs. On the bottom arc, it's G. On the top right arc, it's G inverse. On the top left arc, it's H inverse. On the bottom left arc, it's H. It turns out that these 2 points on the 2 ends are fixed points. And this guy, the North Pole, goes to the South Pole. So under this, it comes here. And you can check that it's actually a continuous map. It's just got these 4 simple pieces. And it's really, I mean, it's not hard to check. I won't do that. It's strange that the core issue is something that you just have to sit down and check. It's not very hard here, but that's what it is. So it's typically, the Bowen series map is typically discontinuous, but for punctured spheres, these are continuous and they have first derivative. I mean, they have a continuous first derivative, which means that this breakpoints condition, which I was getting aggravated about, is automatically satisfied for these guys. And the key thing is that this Bowen series map is actually orbit equivalent to your group. So there's a single map which records the dynamics. So here's the thing, in general, if you have a sphere with k punctures, you look at the associated Bowen series map. The Bowen series map, it's not just the surface, it's the surface and a fundamental domain, which together give you the Bowen series map. I mean, on each piece, it's basically you have these matching guys, and those are the guys that you define on the arcs of the circle, and gives you an expansive map, which means basically topologically conjugate to z goes to z to 2 power 2k minus 3, covering of the circle, and it satisfies the Markov property. The Markov property is easy, right? Because this 1 goes to 1, 1, 1. Yeah? So 1 goes to 3 arcs. That's it. Okay, so this is an example, and it's true for all. This basically tells you that the bound series map is enough to tell you, to give you examples of mating, where on one side you have z goes to z power d, where d equal to 2k minus 3. On the other side, you have the sphere with k punctures. Yeah? That's a hyperbolic object for k greater than or equal to 3. So what have we done so far? It's basically the complex analytic theory. So essentially we started off by trying to combine z to the d and Fuchsian groups, and we were essentially forced into saying that, look, you have to have a framework for matable maps. Fortunately, David tells us there are no local analytic obstructions, and therefore you can, once you have a matable map, you can combine dynamical systems. Yeah? However, are there matable maps consistent with group actions? And bound series gives you examples for punctured spheres. So that's a summary of what we've done so far. But I think there's a little more here that one can say, which is basically you are allowed to have, order 2 orbifold points also. Yeah? So that's one extra ingredient that you have here. Let me, yeah. Okay, maybe if I can. There are problems about topological conjugacy for surface groups that are still open. I think I've advertised this question many times, and I'm very frustrated about it. I'll probably say it at the end. Okay, so now that's this part of the story. And now let's see if we can generalize the bound series examples. And okay, so this is the key point. The bound series map is orbit equivalent to the group, hence a matable map, hence you can combine. Okay, so now suppose we want to go further. Yep. Yeah. That's correct. That's correct. It's not defined on one side, on the group side. It's a piecewise Mobius map. So it's really defined from the disk minus this ideal polygon, finite-sided ideal polygon, onto the disk.
When conjugated topologically holomorphic.
Yeah. So it's conformal. Yeah. So when you've conjugated, so basically you have a self map from the Riemann sphere minus this ideal polygon to the Riemann sphere. That's what you're going to get after mating. There's a hole on the other side as well. Yes. So you're really looking at a uniformization, and then the dynamics of F is pulled back via this conjugation to get a partially defined holomorphic map. The holomorphic map is not defined on the whole Riemann sphere. And yes, so as a sneak preview 2 slides hence, the aim is to try to get it to the whole Riemann sphere, even though we can't directly. Okay. So okay, so now let's try to soup this picture up a little bit, and suppose we have. So I think this can be. So you're allowed. So now let's say that and really the problem is with the bound series map being, demanding that it is continuous. Yeah, that's not how the original maps were conceived of. But measurable stuff on the circle, just measurable maps, are not going to get us anywhere in the complex dynamics world. So what about controlled discontinuities? Yeah? And so this is what this is about. This slide is about. It's basically now. So what is it? So you have a 4-fold symmetry. And here what you're really doing is there's a Z mod on each of these quadrants, there's a Z mod 2Z symmetry, which really takes this side and flips. So basically this is a fundamental domain of the 4-fold symmetry. You take the vertical y-axis and the vertical positive y, and the horizontal positive x, and you paste them together, and you have an orbifold, order 2 orbifold in the middle of one of these red arcs. So what you're going to get is basically, that's 1 order 2 and 2 punctures there. 1, 2, yeah, and if you count all of that together, so that's right. So this is supposed to be, so these centers contribute, centers of these arcs contribute to the order 2 orbifold points, and there's a further 4-fold symmetry. If you quotient out by this 4-fold symmetry, you're going to get 2 punctures and 1 orbifold point of order 2, and one orbifold point of order 4. So this is basically a 4-fold cover of 2, 4, I mean 1 orbifold point of order 2, 1 orbifold point of order 4, and 2 punctures. Yeah? That's the orbifold for which you've taken this 4-fold cyclic cover. Okay, and it turns out that there are discontinuities of this map. So if you look at the Bowen series map corresponding to this, this is also it's a 4-fold sphere, but it's now got, so because of these extra symmetries, you can't quite match them up. The point is that some of these breakpoints fit into nice orbits. So if orbit of a point of discontinuity goes to itself, and that whole orbit is collapsed, yeah, then in the quotient guy, you have still a continuous map. That's the only thing that we are using here. So basically quotient this guy out, and what you get is a factor of this Bowen series map, and the factor turns out to be continuous even though the original Bowen series map is not continuous. Yeah? So I think if you look at these points, you're going to get discontinuities of the Bowen series map, but if you quotient out by this 4-fold symmetry, these 4 lines here go to this one single line there, and the resulting object, the discontinuities have vanished because the points of discontinuity have now been identified. Yeah? So this is a way of upgrading, even though you have discontinuities. If you have controlled discontinuities, you can upgrade two orbifolds where there are finitely many orbifold points and possibly one new orbifold point of order greater than 2. Why is this important? Because the first, so if you quotient under Z mod 4Z, you get a genus 0 orbifold with 2 punctures, 1 order 2 orbifold point and 1 order 4 orbifold point. That's basically the quotient of this by Z mod 4Z. Okay, why is this good? It turns out because I mean, there were these controlled discontinuities and you pass to a quotient, and the resulting guy is still, it's now piecewise continuous, piecewise analytic. Locally, it's got the same structure as a piecewise Mobius map. So this resulting quotient guy locally still has the structure of a mateable map. So you can combine with Z goes to Z bar D. Okay, so the factor map is mateable. So you allow yourself a little bit of breathing space by allowing yourself finitely many discontinuities which lie in a single orbit. And so you can actually upgrade the previous class of examples and allow yourself an orbifold point of order greater than 2. Why is that important? Why is that of any use, and why were we interested in doing that? It's basically because we wanted to capture one example. There was one example which came from correspondences, somewhere from the early 90s due to Bullitt and Penrose. And recently, various theorems about those have been proven by Bullitt, Lomonaco, and then Sabia and Misha and Bullitt and Lomonaco. So I think we wanted to capture this one example in this mateability framework, and that needed us to have, what was that example? That example was basically H2 mod SL2Z. Yeah? There's the one example that was there from the early 90s, and that came from a very much more algebraic point of view, directly through correspondences, not through this complex analytic framework, and then hoping for, so we wanted, at least in this complex analytic framework, this basically tells you that the modular surface, which has one orbifold point of order 3, one order 2, and one cusp, falls into this framework. So that example does fall into this, but you are necessarily required to have this controlled discontinuity there. Okay. So once you have this, so you have this now, this right side picture is basically this factor Bowen series map, and you can mate this by the similar argument by basically this mateable maps are mateable on the outside, and now you have a self map on the right side. Yeah? So this is basically the factor Bowen series is what's going on inside. This hexagon is the whole, and outside you have z goes to z bar d. All right. Now there is this particular map F on the boundary, on the boundary of the whole. What does the Bowen series map look like? So if you look at just the factor Bowen series map restricted to the boundary of this guy, it's an involution because it's basically those internal edges here. See, here what was happening is that this edge was falling onto this edge and it was just being exchanged. So it was an involution on these finitely many edges. Yeah? So the factor Bowen series also retains and has this property on the boundary of the whole, it's an involution. That's a very useful thing to have. Why? Because you now have a self map. You have a self map partially defined on the Riemann sphere, such that on the boundary of this whole, it's an involution. So now you look at the uniformization map of the domain of this self map, which means the complement of this whole. This is a standard uniformization map. Because it's an involution, you can actually extend this uniformization map. This is on the domain of F, which means it's on the outside. This uniformization map, you can extend via this involution inside, and then you get a multi-valued map. So you get a multi-valued map after you do this uniformization, basically because you're trying to extend F over a boundary on which you have an involution. So you look at finally the self map, pull back via this uniformization map R, which takes the boundary, this guy here, to this whole, extend via this involution, and then pull back F via F, pull back F on the right side via this conjugation R. And because R is an extension of a uniformization map, which means necessarily one-to-one on one side, via an extension where what you're using is the z goes to 1 by z symmetry of the boundary, this map R extends to a rational map. I mean, you're basically, so you get a rational map, and now you can pull back your F. So rational maps, and this is really what I was hinting at when I was telling Subhojoy this statement, what this is really trying to do is trying to move from the analytic framework, which is just this mated map, or this map, which was the z goes to z bar d, along with the factor Bowen series map analytically extended. It was just an analytic map, but because this uniformization map is an involution on the boundary, you can do this extension, and there's a little check to be done, essentially saying that the singularities remain zero model. I mean, they don't become wholes. And that allows you to prove that you can really pull back this guy via this algebraic map so that at the end, you have an algebraic correspondence here. So it's basically upgrading. What is this slide supposed to be doing? It's trying to say you can actually start with this map F. It turns out to be an involution on the boundary, which is a circle. Because it's an involution, it's conjugate to z goes to z bar. So you can do a reflection locally, and that is going to give you an analytic continuation. But because it's giving you something on the whole Riemann sphere, possibly with poles, you're going to get a meromorphic function, which means a meromorphic self-map, which means a holomorphic self-map of the Riemann sphere to itself, also called a meromorphic function. That's necessarily algebraic, so it has to be a rational function. And so you can really take this self-map that you have, which was F, pull it back via this R, and you're going to get a correspondence. So again, summary of the story so far, we started with a topological theory, which required all this orbit equivalence stuff, relaxed our framework, allowed orbifolds of order greater than 2 in order to incorporate the modular surface, and then move over to prove that in this particular case, because the boundary of the domain of definition of the self-map of F has an involution, and F extends continuously there, the conjugation can be extended across, and the uniformization map can be extended across, and you get a rational map, which you can use to pull back F, and you get a correspondence. So this is the first, the first time we are trying to address this Fatu's question, basically via this mutability framework. So we have what we want to start off with, the correspondence. But since since we have a correspondence, it's basically the moduli space of certain rational maps becomes significant. But rational maps of a particular degree just have finitely many parameters. So it's got an algebraic parameterization space, and this is where Bers comes in. So what are we doing now? So now we are basically trying to say what the interbreeding story is, but in terms of not individual examples. So in some sense, the dynamical plane is what we discussed so far. What about its parameter space? Yeah? And in particular, what is the Bers slice like? What is the analog of the Bers slice? And you have two analogs of the Bers slice. So basically, you can let your surface sigma naught vary in Teichmüller space. This is the x-axis. Or you start off with z power d, and you can let your polynomial vary in the space of polynomials of degree d on the vertical side. And now, this is now all sitting via this stuff in the previous slide in the space of correspondences. Because it's sitting in the space of correspondences, that's some algebraic gadget. Yeah? So that's some finite dimensional algebraic variety. Inside which, that's the analog. The space of all correspondences of a certain degree would be the analog of the character variety in this setup. And if you keep one of your z power d's fixed, yeah, what you get is the analog of the Bers slice, which is basically z power d on the polynomial side, mated with all possible surfaces in the Teichmüller space of surface with, say, d plus 1 punctures or d punctures. That's the Bers slice, and you have, therefore, the Bers slice sitting as a complex. There's a little bit of work to do to prove that this is a complex analytic embedding, but you have a bona fide complex analytic subset of the space of correspondences. So you have, as in the classical case of a Bers slice, sitting inside the character variety. Here you have a Bers slice sitting inside the space of correspondences. And now this is last slide, which is joint work with Yusheng Luo and Sabya. If you fix F basically in the principal hyperbolic component means polynomials which are obtained by deforming z goes to z power d. And this horizontal Bers slice, this is really Bers' theorem, but where you replace surface group on one side by z power d. Yeah? This is pre-compact. Yeah? So it's bounded in the analog of the character variety, which means in the space of correspondences. And just for n equal to 4, that means the place which has smallest moduli, the surface with surface of genus 0, which is a sphere with 4 punctures, you can, because they are pre-compact in algebraic variety, you can compactify them. And they turn out to be homeomorphic. Yeah? And so this is the classical picture for this is exactly the picture that's there on the poster. Yeah? That's the Bers slice of surface with genus 0 surface with 4 punctures. Except that here, the pictures, we don't know whether they look nearly as nice. So we know they are all homeomorphic. We know that the surfaces slices are pre-compact. We don't know, and this is where there's a whole bunch of things we don't know. We don't know if the boundary of these horizontal Bers slice in n equal to 4, whether this is a Jordan curve. We don't know if it's a topological circle. We don't know the analog of Kirchhoff-Thurston. So if you change a base point in the space of polynomials, oops. if you change the base point in the principal hyperbolic component, do you have discontinuity on the Bers boundary? This is basically a phenomenon discovered in the mid-80s by Steve Kirchhoff and Thurston. You don't know whether an analog of that happens here. What if you allow yourself to degenerate on that? This is stuff I would really love to know an answer to. Suppose you allow your group site to degenerate. Yeah? So this is, I mean, I think Bers apparently, when he came up with these degenerate groups, he said that the group is, the debris of the group is still left in the limit set, something like that. So basically, it's now I think we understand the Kleinian group side picture pretty well, and you have the boundary of the Bers boundary groups are pretty well understood in terms of these ending laminations. A lot of people have worked on, a lot of people's work goes into that. So if you allow the group site to degenerate, what do you get? What's the analog of the double limit theorem? Which means basically now you allow your group to degenerate and your polynomial to go to the boundary of the principal hyperbolic. What are the things that you get? And finally, being a little maybe overambitious here, so you can actually get a handle on even indiscrete representations via projective structures, yeah, where you have a local convex hull. Can those groups with indiscrete representations be mated with Z goes to Z party? And the questions go on. Basically, anything that is answered in the last 40 years about Kleinian groups, you can put into this framework and ask the same question. But it's very frustrating because we don't know the answers. Let's stop there. Thank you. Yeah.
Okay, I think I missed it, but do you recover the bullet Penrose examples?
Yeah, we recover the bullet Penrose examples, yeah, but we get at it from a very different point of view. I mean, so the proof is very different.
Because from my memory, they had this sort of multi-valued
exactly.
map. And so can you interpret your things in terms of multi-valued maps?
Those multi-valued maps are exactly these correspondences. They have two correspondences. That's exactly what we get.
Yes, yes. Yeah. So, but then maybe for DD correspondence.
So I guess,
would that be a degree D map and a degenerator group?
Yes. So I think what we do get would be, for example, I mean, here are the groups that we'll get. You take one orbifold point, so basically Hecke groups, so K, comma, 2, comma, 2, comma, 2, comma, infinity, 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 etc. These are the guys. So we can deal with one orbifold point of more than 2. 2 morally is like infinity, but it's half of infinity. But yeah.
Very good.
Yeah.
Thank you.
So, yeah. Yeah.
Can you just say a little more about the space of correspondences? Because I sort of missed.
Okay. So here's the thing. So suppose you have rational maps. So rational maps would be polynomial divided by polynomial. But suppose you had a correspondence locally, what is it? It's Z goes to nth root of Z, or Z goes to Z power n, and then it's inverse, right? So locally, you will be having n branches. So rational maps of roots and their inverses. That's what you'll be looking at, right?
You said there's an algebraic, forms an algebraic variety, space of correspondences.
Correct. So basically, if you have roots of polynomials, so basically you look at all possible. So let's see. So suppose you want to look at the parameter space is given by, say, let me give you a very simple example, which I can actually nail down here. Let's say you want to look at square root of CZ plus D, or CZ square plus DZ plus E. So then how many parameters do you need? So it's 2 values for this, for the square root. And then you have these 3 parameters, right? So that's going to give you, so the locus of that is going to give you it's not a closed variety. It's an open, algebraically defined subset of a variety. Yeah. So here's the thing.
limit there? Or?
No, so here's what would one like? Okay, so I think this is something I have not talked about here. There are some examples, right, in the
So,
the question is, when we are degenerating, is it cusps alone that are getting pushed together, or is it something else that's happening? Okay, so let's go back to this picture here. Where was the first one? The Bowen series guy. Yeah, this is the picture. Oh, it's already drawn here. Okay, so here's the thing. There are places, I mean, so basically there are some guys you can actually pinch. So for instance, in this, this is not a good picture. So suppose you had one more genus. Yeah? It's basically, instead of a triangle at the top, if you had a quadrilateral. So then there would be, basically from the middle guy downward, there will be one circle that goes round. It's basically the four-punctured sphere, the fat circle in the middle. Yeah? You can pinch that. Okay? So this collection of correspondences allows you to go to the boundary on the group side, provided there's just this finitely many simple closed curves. There's just one vertical, and there's another one which consists of two horizontals. Goes down. It's two pieces in the fundamental domain, but it's one circle. So these are the only two circles you're allowed to pinch in this framework. Yeah? So those do give you cusped objects, but that's still parabolic, guys. What one would really like, and you can't do better than that. I mean, in this Bowen series framework, you can't pinch an arbitrary simple closed curve. Though one would expect that those guys are parabolics, and there should be some reasonable format in which you can do this combination. We don't know, we don't have a fully nailed down version of that yet. What is degeneration? It means basically when the simple closed curves are now replaced by laminations. So basically you know how to take a simply degenerate group by letting one lamination degenerate, so that becomes the ending lamination for that guy. But how are you going to put that Fuchsian group, that degenerate Kleinian group on one side together with Z goes to Z party? Okay. Essentially, you can iterate. Yeah? If you iterate, because of this pre-compactness result, you're going to go to the boundary, going to go to some group on the boundary of the Bers slice analog here. Do you get a mating? Don't know. These should be morally the things that should fit into Fatou's framework, but we don't know.
Okay, so here's some wild speculation.
Yeah.
Long time ago, Caroline and I constructed a Markov map for actually the mapping class group of the twice punctured torus on its Thurston boundary.
Ah, okay.
So therefore, you could extend that onto Teichmüller space on one side, and so could you possibly make that with a rational map on the other side? So now we're talking or analytic map of some sort. So now the Thurston boundary is S3, and so that's now we're gone up into.
I see. Wow.
So you could you could maybe this sort of higher dimensional.
Higher dimensional.
So that would perhaps this is a speculation.
That would be fantastic. Okay, yeah, that would be really fantastic.
This is for some of the younger guys to think about.
Absolutely. That sounds fantastic. Yeah. I have no idea, for the record. Yeah. Okay. Yeah.
Wild speculation.